Hey there kids, this is Math 116, section 5.3, applications of exponential functions and logs. Exponential functions and logarithmic functions. So now we're doing a little bit more of the same. There's more applications and more solve for x types of problems, so you can increase your familiarity with logs and exponents. So this is question number 5 on page something. How's that for being helpful? It says 25,000 is equal to 10,000 times, I'm running out of space, 1.05 raised to the 2x. Get rid of that there. So it's raised to the 2x, and you're supposed to solve for x. Here's the why this is different. Is the x now is in the exponent. Do you see the x is up here? That's kind of a problem. Normally you could just kind of multiply things across and get x by itself, and we still want to do that, but with x in the exponent, we have to use logs to get the x down where it should be, out of the exponent. So the first thing we're going to do is divide both sides by 10,000. We're going to do our best here to get x all by itself. So 25,000 divided by 10,000, we have 2.5 on this side, that goes away. Now we're left with 1.05 raised to the 2x. Well, that's not a lot better, except it's a little bit better because we can take the log. Why would we take the log? I'll show you. And this works with either natural log or regular log. I'll just take log base 10. Take the log of both sides. Why would you do that? Because of this. Watch this. So I'm just going to leave this for now as log of 2.5, but this is actually a number you can plug into your calculator. We'll get that in a minute. On this side, this log of 1.05 raised to the 2x, remember the properties of exponents and log functions. Haha! This is why we do it. Triumph! The 2, because it's an exponent, can come down in front of the log. So this all becomes 2 times log, I'm just using base 10 so I can use my calculator later, of 1.05. And we have our 2x all by itself. Yay! So on this side, I can now divide by log of 1.05. So I get, let me do this on a new paper. Oh look, I got my paint things all backwards. So let's do this again. Here's where we were. Log of 2.5 is equal to 2x times log of 1.05, because that was the exponent and he came down in front. Now we can divide both sides by log of 1.05. Divided by log, base 10, 1.05. So now we have 2x over here all by itself. This number you can type into your calculator, log of 2.5 divided by log of 1.05. By the way, this one's about 0.397, and this log of 1.05 is about 0.211 point. So the whole thing on this side is approximately 18.78. So that gives us a spectacular value of x equals 9.39. Okay, let's look at another one. Here is another one, question number 17. We have natural log of x minus natural log of 5 equals 10. Well, there's a couple of ways to do this one. I'm going to draw a little line here. Here's one way to do it. You can say, well, according to our log properties, this is natural log of x divided by 5. Remember when the subtraction here means you can take these two and it's x divided by 5. That equals 10. Okay, I haven't done anything, I just rearranged the equation. And again, I'm trying to solve for x. This is the problem. What is x? Okay, so because of this natural log, to get x by itself, we do this trick. Raise to the e. So we have e to the natural log of x divided by 5 equals e to the 10. Okay, why would we do that? Because e raised to the natural log of something is just the thing. So this whole side turns into x divided by 5. Right? Because it's e to the natural log, which is log base e, of x divided by 5. That whole thing equals x divided by 5. So now we have x divided by 5 equals e to the 10. Multiply both sides by 5. And I get x equals 5 times e to the 10. This is the answer that your book gives you. Aren't they clever? This is another way you can do it though. in case you're doing it this way and you think, I got stuck. It's okay, you're on the right track. You can do it this way. You can say, well, natural log x equals, natural log of 5 is just a number. So if you want, you could just stick the natural log of 5 over here. You could add natural log of 5. Be 10 plus natural log of 5, like that, which you can do on your calculator, and that equals something like 11.609. Okay, so if you got this far and you think, oh great, now I'm stuck. You're not stuck, my friend. You can get out. All you do is raise to the e. So the way you get rid of natural logs is you raise everything to the base of that, whatever the base is. So in this case, this is log base e. So we raise everything to the e to the natural log x equals e to the 11.069. On this side you get x equals, whoa, and it's some big number. Some big number. Let me do it here. I have 10 plus natural log 5, yep, 11.069, and I'm saying e raised to that answer. I did it before, I just wanted to check again. 11.0132, sorry the comma's there, 0.329, something like that, which is approximately equal to e times 10, e to the 5 times e to the 10th, la la la. So there's two ways you can do this one. There's one more I wanted to go over. This is these population growth functions. So this section also deals with a lot of population growth because those are exponential. So question number 32 says the population of a certain city grows according to the formula y equals p0, and in these p0 almost always stands for the initial population, the population at time 0, and then e to the 0.03 t, where t is some year. So again, in this case, P0 equals the initial population. How would you know that? Well, I'm going over the problem. That's how you would know it, because you've seen a problem like this before, because we're doing it right now. So this is very similar, and then they give you, if the population was 250,000, make sure that's right, and not that it's million. Yep, 250,000 in the year 2000. Estimate the year in which the population reaches 350,000. This is really similar to example 4 on page 353. So just so you can look at that if you like. So here's our formula. We have y is equal to p0 times e to the 0.03 t. Okay, and they tell us that the population, so this is right here, that's the population, and t equals the year. So what you can do is you can let year 2000 be t equals 0. Let that be year 0. Okay, 2000 be t equals 0. So start counting at the year 2000. The reason you can do this is because if t equals 0, we'll say we'll start counting at the year 2000, then we know the population is 250,000, because we don't know this P0. So our first goal is to find out what that is. Okay, we need to get a number for this one. So P0, e to the 0.03 times 0, if we let the year 2000 kind of start the clock there. So then this is all just 1, because e to the 0 is 1. The reason I did this is now my equation is a lot simpler, because I have P0 equals 250,000. We're done! No, we're not done. I just added more information to our equation. So now the equation looks like this. Y equals 250,000 times e to the 0.03 t. So now we have more information. We used the information that in the year 2000 the population was equal to 250,000. We used that to find P0. That was step 1. Step 2 is going to be let the population be equal to 350,000 and solve for t. So what we really want to know, if you go here, is what is the year? So find t when y equals 350,000. Like that. That's what we want to do. Over, where am I? Here. So, y is 350,000. Nope, here, get rid of that. 350,000 equals 250,000 times e to the 0.03t. Now we have to solve for t. Let me get a new page. File, new, don't save. It's white. I don't like white. I think it's easier for you guys to see if I use a black screen. So here we have 350,000 is equal to 250,000 times e to the 0.03t. We're solving this for t. So the first thing you can do is get rid of this 250,000, divide everything by 250, divide this side by 250,000. Exciting, isn't it? What's going to happen? Divided by 250,000 equals 1.4. Equals e to the 0.03t, because that's 350,000 divided by 250,000 is 1.4. Okay, now we have this 1.4 equals e to the 3.0 or 0.03t. So the way you get rid of this e is you take the natural log. You just kind of go back and forth between natural logs and raising to the e to get rid of these various things like this. So we take natural log of 1.4. So this, because we're taking the natural log of e to the something, that just turns into 0.03t equals natural log of 1.4, doing it again on my calculator, 0.33. I suspected as much. These you have to use a calculator for. So the natural log, in your calculator it looks like this, of 1.4. Divide both sides by 0.03. And you get t by itself. That's what we wanted, people. It's happening. T equals 11.21. So, before you just circle it and move on to the next problem, remember that we let year 2000 be t equals 0. So now for our final answer, we're going to have, this is going to be, our final population is going to be 11.21 plus 2000. So the answer is 2011 plus a few months. So I would accept, if on a test, either 2011, or if you wanted to say 2012, I'd probably accept that too, because you're a little ways into 2012. So again, to summarize what we did for this problem, first thing we did is we took the information that we had and we said, well, let's let the information that we have be the starting year, t equals 0. So we used that information to solve for p0, and that gave us a better equation. Then we said, let's solve for t when this side, y, the population, equals 350,000. What is the year? And the answer is the year is 11 or 2011. Whew! So look at those problems and let me know where you get stuck.